Um, so my goal today is to talk about water mass transformation, and then tomorrow I'm going to talk about air-sea interaction. So these were both topics that were allocated to me, and I've made a sort of arbitrary decision to do the water mass transformation part today and air-sea interaction tomorrow. So I'm going to really try and address three questions. One is, how is the Southern Ocean changing, and how do we know that it's changing? The second, what specific processes drive the change, and that's going to lead us into what's referred to as volume analysis. And where are the future challenges and opportunities? I have to apologize at the beginning because there is no way to get this to be pitched perfectly for all of you. And so I'm going to get it wrong. But feel free to stop me. Let me know if we need to spend more time on something or if I need to hurry up. So I'm going to start then with, how is the Southern Ocean changing and how do we know? And that's really a question. I'm going to take us into observation world. And a lot of this comes out of Argo. Argo floats are the robotic systems that have really transformed our ability to see the ocean. And that includes core Argo, which measures temperature and salinity. That's the central part of the Argo program. Deep Argo floats, which are encased in glass spheres so that they can go to the bottom of the ocean and not implode. And biogeochemical Argo floats, which are not supposed to be part of what I talk about, but I will anyway. So if you're familiar with Argo, this is old hat. But the basic concept of an Argo float is that they're dropped into the ocean from a ship. So they have this antenna at the top, but they descend down in the ocean to about 1,000 meters depth. And then they just drift along with the ocean currents for about 10 days. And at the end of 10 days, they go deeper to 2,000 meters. And then they come up to the surface. So they get a clean, single profile from 2,000 meters up to the ocean surface. When they get to the surface, they do what any of us would do when we emerged from 10 days in isolation. They send a text message. And they say, this is what I measured. This is the temperature, this is the salinity. And then they repeat the process. So they do that again and again, and they give us these profiles of temperature and salinity that tell us what's happening across the ocean. And Argo has been an enormously successful program. There are currently close to 4,000 floats in the global ocean. And they cover a broad range of areas, including places that are seasonally ice-covered, and they operate year-round. So they give us a way to map ocean properties. This is mapping, taking all those Argo data and producing a gridded map of temperature at 100 decibars in August. So we can produce these maps that give us gridded data over the Argo record. And of course, we can think of this as in many ways to average this. So we can integrate temperature then over the top 2,000 meters of the ocean. So you can imagine taking temperature anomalies measured by Argo and integrating them from 2,000 decibars to the surface. So we're going to look at just the top 2,000 decibars. We get the temperature integrated over that area, and we can look at what's happening. So that gives us a measure of how the average temperature in the ocean is changing over time. So here this animation is showing us the evolution of global temperatures from climatology mapped from Argo data over the global ocean. And so we see how temperature is changing. These are, you can see the temperature scale here is going sort of from, well, it's really concentrated in sort of plus or minus 0.3 of a degree. So they're comparatively small changes integrated over 2,000 meters in depth. But when we look at what happens over time, so this is from the real start of the Argo program up to the most recent map or plot that was made. This is over the global ocean, and it's showing us the temperature change, so integrated spatially over the global ocean. And what we see is that the ocean has warmed over this time period. So it has gotten warmer and warmer. When Argo started in 2000, the temperatures were clearly colder than they are now. And that's a pretty sobering change. It is not a big temperature change. You can see this is something on the order of 1/10 of a degree or less. If you stuck your toe into the global ocean, you wouldn't be able to tell the difference. But it has a lot of distinct characters. So one thing we see looking as a function of time is, of course, that this temperature change has evolved with this steady rise in temperature over time. There's a very strong seasonal cycle to it. And it's useful in looking at this to ask, when is the global ocean warmest? What time of year? So I'll give you a moment to look at that. What did you say? What time of year is the global ocean warmest? We see this temperature cycle as a function of time from 2005 up to the present. Austral summer. Any other guesses? Yeah, austral, it is, well, the important thing is to note the hemisphere. It is, and it's, so here's, let's see, 2020, we can line up. This is happening in sort of January, February, March. So it is austral late summer and austral fall. And that's our measure of the fact that the mass of the global ocean is in the southern hemisphere. So if you want to know where the ocean is, it's the southern hemisphere. Of course, that's the part that's going to dominate the seasonal cycle. But the other part of this is that the warming is concentrated in the Southern Ocean. So this is from this paper by Rembeck et al. That really put this together. It's from 2015, but nothing's changed since then. And so this plot shows the temperature trends in black for 60 south to 20 south. And you can see that that's shown a really steady warming from 2005 to 2014. And then the other blue lines, I've never managed to label them, but one of them is the tropics and the other is the northern hemisphere. And in essence, it doesn't matter which is which because there's nothing happening. All the warming in the global ocean is happening in the Southern Ocean. And that's our reminder that all these processes that we've been talking about this morning that lead to the overturning circulation, the structure of the Southern Ocean, how it interacts with buoyancy forcing, are really critical to understanding how the global climate is changing. So now you might say, this is sort of limited. We got Argo going, and the Southern Ocean was the Cinderella of Argo, so it took a while to get going in the Southern Ocean. But Argo started going around 2005. We have a record from then on. What happened before then? And the answer, of course, is we really have lousy data. So this is a map showing, this is showing all of the profiles collected in the decade of the 1960s, from 60 south to 40 south. And you can see that there were a fair number of profiles in those 10 years. There's some gaps that were not measured at all, but there are measurements. But in contrast, this is what happened in a single year in 2010. And the difference is really remarkable. It tells us that now we really know what's going on in the ocean. But before this, our data are so sparse, we have a real risk of misunderstanding or missampling the data. And so that means if we want to go back in time, we have to think very carefully about how to use the historic data. The modern data we can make nice gridded fields from, but the historic data are just not really dense enough to justify doing a mapping exercise. So we're looking at something like this. Historic data are something like these magenta profiles. They might be in different places relative to the frontal features of the circumpolar current. They are far apart. They don't make sense. But with the Argo period, we have clean gridded data that cover a complete grid. And so what we can do is to interpolate the gridded values onto the Argo locations and then look at the differences between those. And so that's what I'm going to show you. Taking temperature profiles from single isolated historic profiles and comparing them with mapped profiles. So if we put that together, and this is one way to look at it. We're looking as a function of time now from 1900. There really aren't a lot of data then, up to 2015 or so. Over 2,000 meters depth, the cross-hatching says things are not necessarily statistically significant. What this tells you is that, well, it's almost all blue. It's telling you that in the past, the ocean was colder than it is now. So we see this steady warming of the Southern Ocean, except right here in the ocean surface. And that might make you think that this is something Matt talked about earlier, and you know what's going on, but this is actually north of 60 South, and it's not what he said. That's actually because people don't like to go to sea in the winter in the Southern Ocean, and so the historic data are completely biased to the summer months. But Argo floats are perfectly happy to operate year-round. And so the difference means that, if I go back, the historic data are completely biased in their sampling to get only summer months. And so they are warmer. When we correct that effect, you can see that really, really it was colder in the past than it is now. So we see this steady warming. We can also look at salinity. Salinity is really a tough quantity. It was measured really badly, so everything is cross-hatched and not believable until about 1950. But what you see is evidence that the ocean was, in many areas, saltier in the past than it is now. So it has gotten fresher, and that shows up with saltier conditions in the past at the surface and at mid-depth over time. So we have evidence that the ocean has changed in really interesting ways. And then you might say, well, do we believe any of this? So this is a different mapping of the same thing. So this is taking the same data, pretty much the same analysis, but plotted in a different way. So Neil Swart took this and said, let's just look at the Argo temperature from 2006 to 2015 minus the historic data from 1950 to 1980. And you see now, as a function of depth and latitude, this evidence for really systematic warming and for these changes in salinity where there's been a freshening of the ocean through a large area spanning a broad range over this time period. And so this was helpful because Neil also had access to the Canadian climate model. And so he went through and did an exercise and said, okay, well, with the climate model, we can look at the whole ocean. So here's the temperature trend for the global ocean, completely gridded fields. And then we can also subsample it as badly as the historic data subsampled the ocean. So that's what we see here. And reassuringly, they don't look wildly different. So that's saying that as horrible as the historic data are compared with what we can do now, they don't give us a completely biased picture of how properties might have changed over time. And then we can compare that with the actual observations, and you can see that the climate model is not wildly in disagreement with the observations themselves. So that gives us some confidence to look at what's going on in the model. And then finally, and I don't have the figures here for it, we can go through and ask what does the climate model attribute this change to? And in essence, so you could imagine that if you have this sort of change in the ocean, it could come as a result of advection within the ocean, or it could come as a result of air-sea interaction. In the climate model, it is completely attributed to air-sea heat fluxes. So we see increased heat flux into the ocean, and that's driving the change. So one thing we can do then is to ask, okay, if we've got this change in the ocean where it was colder in the past, it's gotten warmer over time, what does that mean about the net flux into the ocean? So we can take this and integrate in depth over some range and integrate in time and ask how much heat would you have to put into the ocean to get what we observe. So I'm going to do that here. And so I should have said, this is now, because I showed you temperature initially and then heat. So for heat, we have to multiply by density and specific heat, but it's basically the same quantity with these scale factors. So if we look over time, and depending to what depth we integrate, we can ask how much heat would you have to put into the ocean steadily over, say, since 1950 to get the sort of temperature change we see. And the answer is, if you integrate to 300 meters or 500 meters, you have fairly similar answers that target somewhere around a half a watt per meter squared of heat input to the ocean. So that's telling us how much heat flux we actually need to explain the observations. There are better analyses of these that come up with fairly similar numbers. And so we know that we have to put heat into the ocean. We can ask the same thing about freshwater. We see a freshwater change. So how much freshwater would we have to put into the ocean? And what we see over time, this is obviously a lot noisier because salinity measurements are more problematic, but the net change is consistent with something like a half centimeter per year of freshwater input into the ocean, or a freshwater input of about 0.01 spheredrops of excess freshwater into the ocean. And so that leads to this question that we can keep asking: is this ice melt? Is it precipitation? It's a good open question. And then we can ask more specific questions. And I think this paper that Matt showed earlier and that I showed at the beginning comes back to this in a really nice way. So Jean Lee, in this analysis, went through and looked at the change in global heat content. And so asking how many joules have to go into the ocean for 2000 to 2010 and 2010 to 2020, showing this net increase in global ocean heat content. But then asked, where does the heat have to go? So where do we deposit it in the ocean? Got a problem here. Go away. And so what was a really nice aspect of the study is that you can look at the ocean heat content change over the top 2,000 meters and see from 2005 to 2023, 2022, this steady increase in heat content. But then they said, let's look at the global ocean in terms of layers. So we can have a tropical water layer and a mode water layer and an intermediate water layer, and ask how much is the heat content changing in each of those layers. And what this shows is that the tropical water layer is really pretty boring and not changing much at all. And the mode water layer has this amazing increase in heat content. And intermediate water, not changing so much, maybe a little. And then they actually divided this up into density classes, and so you can look at the change in ocean heat content as a function of density class over time. And what you see is that this warming really is concentrated throughout this mode water layer. So the mode waters are where the heat is coming into the ocean. So that's giving us a perspective on how the ocean is changing. Edgy room has decided it's going to mess me up. So now I want to take a different perspective on this. So we've looked at heat, and I also want to spend a little time talking about pH, because Argo has given us the same sort of perspective that it gives on heat. It gives us to look at ocean acidification. So biogeochemical Argo floats measure pH, oxygen, nitrate, chlorophyll, fluorescence, backscatter. So this analysis that Matt Masloff and Ariane Verdi coordinated really looked closely at the pH changes from Argo data. So here we're looking at, this is complicated. The background is from a mapping effort. The circles that have black around them show measurements from biogeochemical argofloats, and the circles that have white around them show measurements from GLODAP version 2, which are older in time. And so you can look at the differences between those, the mapping minus the mapping from the modern data minus the GLODAP data. And what you see in these differences is that the circles are mostly blue, implying that over time the ocean has lower pH. It's gotten more acidic. And to really plot this out, here are plots then sorting by depth as a function of time. So we're going from 1990 up to 2020. And you can see that regardless of depth layer, these fitted lines show that the ocean has gotten, the pH has dropped. The ocean has gotten more acidic. That's also true pretty much regardless of which part of the ACC you look at. So subtropical zone, subantarctic zone, polar frontal zone, everything shows these decreasing lines. So we see this pH change over the ocean. So we can look at how this is structured. So here we're showing the number of observations on the left and the pH trend as a function of frontal feature and depth on the right. And you can see that there's quite a bit of structure to how the pH trend has evolved. What's striking in this plot is that this color bar is actually a divergent color bar. It's just that the positive part is gone because there's nowhere where the pH has gone up. It is always decreasing. So it's a massive increase or decrease in pH. And so what was helpful then was to overlay the sort of overturning structure that we've been looking at earlier today on top of the pH trends. And what you see is that what we see is where the pH has not decreased so much is where we expect that water might be coming up from the deep ocean. Where there is mode water formation, where water has been in contact with the surface recently and is sinking, is where we see these strong decreases in pH. So there's a really nice link between the sorts of climate trends we see and the large-scale circulation. So that leads us to asking, if we've got all this change happening, how do we really diagnose what specific processes drive the change? And so there are a couple approaches you can take to this. One is to just imagine doing a full heat budget in a chunk of ocean. So here's a sector of ocean. We can cut it into a square. And we can ask how the time rate of change of the ocean heat content, so that's related to density times heat capacity times the time rate of change of the temperature integrated in space. And we can look at that in terms of all the things that might be driving it. Air-sea heat fluxes, advection, entrainment into, say, across the base of the mixed layer, diffusive processes, radiative fluxes. So we can put all of that together and try and put together a budget. And we do that, and it's worth taking a look at that. So I'm going to take a moment on that. If you look at the mixed layer heat content, so we can ask what the time rate of change of mixed layer heat content is. This is just the seasonal cycle. So we're looking as a function of month. And we can compare that with the heat fluxes, the climatological heat fluxes that go into the ocean. So here, looking at heat fluxes from NCEP and ECMWF, there's a red line and a red dashed line. They pretty much agree. So they're pretty much showing the same amount of heat going into the ocean. And what you see is that there's a reasonable agreement between the net heat content in the ocean, in the Southern Ocean, this is 40 to 60 south, and the heat flux, but they don't fully match. There's a slight mismatch in this. And so you might ask, what would it take to make this work? So that was mixed layer heat content. Here I've added another line. This is the light blue line shows the heat content in the upper 200 meters. So we've just gone a little deeper than just mixed layer heat content. And now we see a really good agreement between the heat flux going into the ocean and the, on the seasonal scale, and the change in ocean heat content on a seasonal scale. So there's a really clear that you have to integrate deep enough to understand how much heat is going into the ocean. On an annual scale, that means going to 200 meters. If we're looking at long-term climate trends, we probably need to go a lot deeper than this to understand what's happening in the ocean. But that there is a balance between the heat fluxes and the input, and the change in the ocean. So that's all good, but then we might ask, what happens? We've been looking at these structures of the ocean that have mode water formation, this whole process of having wind stress at the surface, a northward Ekman transport, heat loss leading to dense water formation, and sinking mode water formation, this whole process that that David talked about, and that is really part of the overturning circulation, even the pH trends that we've looked at. And so when we think about that, you might say that this notion of just taking a box of ocean and trying to do a heat budget doesn't really quite make sense. We should be looking at the changes in the ocean within a framework that takes into account the isopycnal structure of the ocean. And so that's what Wallin analysis is intended to do. So this is a framework that says, let's look at a volume of ocean separated by two isopycnal layers. So we've got one isopycnal that does something like this, and one here, and we're going to look at the change in the volume over time, or in that layer. So you could then ask, so we've got a flux across from a transformation happening from one density class to the next as A of sigma 1, and another one A sigma of T. And then the other thing that's going to affect the volume is any flux that goes out the edge of the domain. So that's the basic framework for this. And then we can ask about transformation by looking at as A is the dipycnal volume flux. So if we're looking at what happens across A, we need to know something about dipycnal mixing across this, and also about the surface flux, F, that goes into that class. So we can put that together, and then from that draw, and that gives us a way to look at the dipycnal water mass transformation. So this quantity M is related to the difference in dipycnal transformation as a function or per unit density. So if we can diagnose that, we can say something about really what's driving the change, taking account of where water outcrops and how it's responding to the ocean, to the processes driving it. So it can be a little tricky to look at from data alone, but what data does do, so this is looking at density class layer thicknesses. So we're looking here at a sequence of density classes going from 26.55 to 26.65, so relatively light water, down to 26.95 to 27.05, so relatively dense water. So as we sink through the ocean into deeper or denser classes, what you see, and you're looking at the thickness of the layer of those classes. So what you see is that as we go denser and denser, we're moving to water that is further east. So moving around the Antarctic circumpolar current, and a thicker layer. So we see this evidence of mode water forming appearing consistently on the north side of the ACC, consistent with this northward Ekman transport and water mass transformation with air-sea heat fluxes, and progressively more water deeper and further poleward as it progresses around the ACC. So, but then I think what's interesting is to take that and ask, can we actually do a full budget And to do this, Surowiecki and Maslow went through and used a state estimate. So they had the Southern Ocean state estimate, and they did a diagnosis on the full fields for this. So they could then look at formation as a function for surface density flux, formation due to diapicnal ocean mixing, a storage term, and a divergence term. And if you look at these four terms together, what's driving the water mass transformation in the ocean, you can see that most of the excitement is happening in the surface density flux. So surface fluxes matter. And that a lot of that is balanced by advection, but that the formation by diapicnal ocean mixing is also relevant. You can't neglect it. And there is some storage. So this is a fairly clear picture of what's controlling water mass transformation in the ocean, how it's changing. So then they could put together as in this mode water class of water, what's actually changing it. So these are transformations in sphere drips. At the surface, you can see effects from cooling, transformation from lighter water, thermocline water, and intermediate water. So there's a cooling effect, a freshening effect, and then there are isopycnal effects or diapicnal effects, cross-isopycnal effects at depth that include warming and freshening. And they put all that together and come up with a full budget for what's happening. So giving us a picture that, in fact, the total transformation is about roughly equal due to surface transformation and interior transformation, 7.9 sphere drips and 8.8. So now the question you might have, you can look at this is all done with a model, it's a way to get a budget to close. What can we actually do with observations? And you can take pieces of this very effectively with observations, but to actually get the budget to close, you have to make some strong assumptions to work with observations to say, okay, we're going to figure out, based on sparse observations, what the advection should be out of one end of the domain. So it's very nice to do this with something like a state estimate, a model that has all the fields, but not so easy otherwise. So I'm going to wrap up here then by asking about some future challenges and opportunities. And I think I've managed to keep things relatively short today, which will get us to lunch not too late. But one concern is Argo has really been a big part of understanding what's going on in the ocean. What do we do if Argo shuts down? And so there's a really important need to support the continuation of the Argo array, including core Argo as well as BGC and deep floats. And what I'm showing here is a plot showing the total number of floats, which is the gray line here. And you can see that this is up to about 2022 from a paper by Boyer et al. The total number of floats peaked a few years ago. It is not going up. And the orange line is showing the total number of first cycles, so brand new floats. And that has also been fluctuating a lot. It is not going up. The Argo array has faced really severe issues due to level funding or decreased funding from partner countries, and funding challenges in the US. The BGC cost of BGC floats has been challenging, and the BGC floats, as valuable as they've been, do not have a clear pathway for a continued global array. And so there's a real issue that as a community we need to speak up and find ways to keep Argo going if that's what we need for our measurements. A second issue is that if we really want to understand water mass transformation budgets, we want to, it's great if we have a closed model that we can work at, but so where the model fields close. But if we really want to understand it from observations, one of the biggest gaps is understanding surface fluxes, and that's the topic for tomorrow. So I'll talk about some of the challenges then. And then finally, there's a question of scale. I've been talking about, in fact, most of what we've talked about so far today has been fairly large scale, but there are there's real excitement at what happens at the submesoscale, and that's what Seb Swart is going to address later on. A lot of the water mass transformation, the processes we're looking at really take on new dimensions when we look at the scale of submesoscale processes. And a lot of the transformation that probably matters is depending on physics that happens at these very small scales. So I'll just quickly summarize. How is the Southern Ocean changing and how do we know? Well, Argo data show evidence for warming, freshening, and acidification in the upper ocean. What specific processes drive that change? Analyses of the overall transformation, so formation, water mass formation and transformation are associated with air-sea fluxes within outcropping isopycnals as well as dipycnal exchange. And there's ample opportunity to do more. So I am happy to take questions, and we can talk more.